Anybody have any questions before we get started? Any past material, uh, assignments, due dates, any of that kind of stuff? Hmm. It looks like y'all can hear me, so that seems to be okay. All right. Well, I guess that's enough people. It is time to go ahead and get started. So I'll ask again, anybody have any questions on chapters 1 through 6? We are essentially finished with the gravity chapter. There's enough examples on my YouTube channel, and as well as the ones I pointed out to you guys on in your Canvas page. But between that and you doing your book and doing your own homework, you should have found everything you needed. But make sure you ask me if you have any questions on that material. We do have a online test. Hopefully you notice I did make it and I posted it and a practice test, and I pushed the due date to a very reasonable Sunday evening of this week. So, or next week, depending on whether you consider Sunday next week or this. But so, anyways, just make sure you pay attention to those deadlines. You've got an online test that's due. I've pushed several of the homework assignments back, so check those as well. Remember, never, never, never never trust the due dates that are listed on Canvas for your homeworks because, for one, I never type them there. They just sort of get filled in automatically somehow, so through some magic of gremlins inside the computer, I guess. And two, they told me specifically never put a date on them in the Canvas system. And three, even if there is a date, it's highly unlikely that it would be correct. So just go to the MyLab and Mastering site and check those dates. Now, be advised, we today will be starting chapter 7. So if chapter 7 was already due, then you know that's not the right date. If chapter 8 is already due, we haven't covered that either. So whatever date it has on it is wrong. Whatever date chapter 9 has on it's wrong. Whatever date chapter 10 has on it's wrong. Uh, but it might have a tentative date that might actually be correct once we start covering it. So just know that I'm not going to assign a homework set and have it due before we've even started covering it. And normally I give it at least one day, but usually two class periods per chapter. And we essentially go in order. I go through chapters 1 through 11, then I jump to 12, no, to 13 and 14. No, it might be 14 and 15. I can't remember. Anyways, but I do jump to simple harmonic motion, which I think is 14, and then 15 is waves. Uh, so whatever those two chapters are, whether they're 14 and 15 or 13 and 14, those are the ones we go to after chapter 11. But pretty much other than that jump, I go in order. So does anybody have any questions? And this is the first time I've yawned all day. I don't know why I'm yawning now, but anyways, I'm yawning again. Yay. Okay. Well, we're going to get started, and we're going to get started by introducing you to a concept called work. And I'm also going to introduce you to a concept called the dot product. And the dot product is a way that you can combine two vectors that's sort of like multiplication, but it's also called a scalar product because it basically takes two vectors and spits out a scalar. So that's one reason they call it a scalar product, but another reason they also call it a dot product, and the reason why they call it a dot product is because you usually indicate it by a small dot between the two vectors. So A dot B would be the dot product of A and B. So we're going to do that. We're going to talk about the work energy theorem and conservation of energy. All of this is really just a way of doing problems that we've already learned how to do, but without dealing with vectors. So it has that advantage of not dealing with vectors. Yeah. Now, that doesn't mean there's no vectors at all. In fact, for instance, we're often going to have to still do a summation of forces in the y direction so we can determine the normal force. And that would be because the normal force is used to calculate friction, and friction sometimes does work on a system. So you might actually have to include it in your quote unquote conservation of energy calculations. So to get started, let me go ahead and share my iPad with you guys. And again, ask me any questions if you have them, but I'm going to go ahead and share my iPad screen real quick. Okay, so here's my iPad screen, and I want you to think in terms of maybe mowing the grass. Because we're going to introduce a concept called work, and that concept work is given the symbol W. And in everyday life, we often use the word work, and it helps sometimes to think about work in terms of what we would consider everyday work. So if you're talking about cutting the grass, you might, for instance, have a lawn that's shaped like this, and you might have a mower, for instance, that happens to be about that wide. In which case, if this were, say, 100 feet, and this were, say, 75 feet, then basically you would have to walk this way for 100 feet and then back this way for 100 feet and then back this way for 100 feet and so on and so forth. Now, in looking at that, you see that there is at least one thing that's going to dictate how much work you do, and that's really the distance that you walk. So I think you might reach the conclusion that work uh, doesn't help that I used red. You might be able to reach the conclusion that work is directly proportional to the distance you have to walk. So in this case, D would equal 100 feet times 1, 2, 3, 4, 5, 6 times 6 paths, and that equals 600 feet. Now, if you had another yard that was, say, twice as big, let's say it too went from here to here, but instead of having just 6 squares wide, it had 12 squares in width. Okay. So this would be 100 feet again, and this one would be 150 feet. Now, in this case, the distance you would travel would be 100 feet times 12, which would give you 1,200 feet. So I think you would agree that it's not unreasonable to say that mowing the lawn on the left is half as much work as mowing the lawn on the right. And that's what that's what work being proportional to D means. Now, if you imagine mowing, let's say just the left yard, if you just imagine mowing the left yard with a lawnmower that is a push mower and it's fairly light, it's got really big radius wheels so it easily goes over small holes and divots. It's spread out pretty well so that you don't have to worry about the mower deck digging into the ground and stuff like that because the big wheels keep it above all that good stuff. Now you might say, what about if instead of cutting that small yard on the left with that mower, what if I replaced it with a much bigger mower that weighed, say, twice as much and therefore was twice as hard to push? It's not necessarily easy to say that just because it's twice as heavy, it's twice as hard to push, but there are scenarios where you could imagine that. If you did that, I think you would conclude that the work is also directly proportional to the force that you're applying. So, for instance, if that second lawnmower was twice as hard to push as the first one, then mowing the lawn on the left with the first mower would be half as much work as mowing the lawn on the left with the second mower. So that gives you a couple of good ideas of what work is related to. But I'll tell you that one thing we want to think about is when we're pushing something like a lawnmower and we want to push it north and south, if there's any component of the force that I apply to the mower that isn't purely north when I'm going north and purely south when I'm going south, then that component's wasted. So, for instance, if I'm pushing down on the mower in addition to pushing north, then yes, the north part is going into the work, but the downward part is just going to making the normal force larger and therefore making the friction force larger and therefore making it harder to do work, but it's not contributing whatsoever to the actual work done. So, what we really want to think about is instead of just being proportional to the distance traveled and the force applied, we want to think of work as equal to the force that is parallel to the displacement vector d times d. Okay? So if you imagine, for instance, let's consider pushing a box or a lawnmower over a level surface, something like this. So you could put a box or a lawnmower or something like that on this level surface, and if you pushed purely in this direction, then F would be parallel to D because the D is going to be the displacement vector for you to push it from here all the way to here. So that's your D, and notice the F is parallel. But if instead you had a force like this applied to it, then that force F has a component that is parallel, that would be this one down here, and a component that is perpendicular, and that would be over here. And in fact, if you wanted to put the vectors tail to tail, what you'd have to do is you could imagine a dotted line, and then we could pull this dotted line a little bit back that way, and then I could take my green vector and draw it again, because drawing it now, I'm drawing it actually at the position where the tail of the two vectors are adjacent to each other, so they're touching. So these two vectors are now tail to tail, and this angle right here would be theta. If you look at this triangle, you'll see that that angle is theta, but that's the same as this angle. So, let's see, is that the same as this angle? No, that's not the same as this angle. Let me undo that one. That would be the same as, oh, sorry. That would be the same as this angle, which would be the same as this angle. So you'd see that F, the component of F that's parallel to D, would actually be F times cosine theta. So if we add a cosine theta to it, or we add those little parallel marks, then that tells you a little bit more about how to compute the work. We've got to take the component of force that's parallel to the displacement and then multiply that by the displacement to get the work. So another expression would be work is equal to F times D times cosine theta, and this is when the two vectors are tail to tail. Oops, left out an I. Let's see if I can. There you go. Tail to tail. Okay, so that's another expression. But what happens if while you're, say, mowing the lawn, There's some patches of grass that are harder to cut through than others, so that the force actually changes. And in the most generic sense, it could be even a case where the force acts in an entirely different direction in addition to having a different magnitude. If that's the case, then what you'd have to do is break up the little path that you're walking along or working along. Let's say it's an imaginary path like this. You could actually break it up into little segments like this. And when you made the segments and you went back and checked what the force would be in each of those segments, if you discovered that the force is identical from the left end to the right end of every little segment, then you've made the segment small enough to do what you want to do. So then you just have to take, for instance, this little dl vector, and let's say this little x vector, and I'm going to call this, actually, I'll call this dl sub I, and I'm going to call this f sub I. And I would then, of course, take the angle theta and I'd calculate f sub I dl sub I times cosine theta, and that would give me the work done for just this one itty bitty piece right here, right? So if I've actually divvied the path up small enough that all the individual forces are constant over the whole interval, then I've made it small enough. If not, if I find, for instance, that maybe one of these segments, let's say this segment right here, if that force varies by quite a bit from this side to that side, then I'd have to divvy it up even smaller so that each one has a constant force with a constant direction. But the main thing is, in that case, then the total work done would be the summation of the individual f sub I dl sub i's times cosine theta. So that's what it would be. So if we wanted to actually do that, then our work total would equal the summation from I equals 1 to n intervals of f sub I magnitude times, let's call it delta L sub I times cosine theta sub I, like that. Then we could add all those up. And in fact, the generalization of all this is that's if the force is a constant, you can use the red box area. But if the force isn't a constant and in fact varies from place to place, then you're going to have to do something like this. Work is equal to the integral of f. Now I'm going to succinctly include that cosine by introducing a new sign. And that sign is that dot right there. And I would say dl. This is what's called a line or a path integral. Okay. And this part right here is called a dot product or a scalar product. Now, that's something that mathematicians and physicists have found to be very useful in the field of vector calculus. Therefore, I can go ahead and tell you that the A dot B can be calculated a couple different ways. One, you can take the magnitude of A, which can be written with absolute value bars around it, times the magnitude of B times the cosine of the angle between them. Again, you have to imagine the vectors have their positions such that A and B are tail to tail, and then this smallest angle is theta. So that's the way you compute it. If you look for a second, you'll see why this works. Let's look at this particular vector. This will be F. And let's look at this particular vector. This will be D, like that. And notice they're tail to tail, so automatically that angle is theta. Now, you can imagine breaking F up into a component that is perpendicular to the displacement vector and a component that is parallel to the displacement vector. So this force right here is F parallel because you see it's clearly parallel to the D. And then this component right here is F perpendicular. And you can see that because it's clearly making a 90-degree angle with the displacement vector. Now, if you look, you will see that D dot F would actually be D times F times cosine theta. That theta didn't come out so good. D times F times cosine theta. But if you look at F cosine theta, you'll see that that is in fact F parallel. Does everybody see that? So you're looking at the little blue hypotenuse of a triangle with the two green legs. One green leg is parallel to the displacement vector, so it's written F parallel, and the other one's perpendicular, so that's written F perpendicular. So are y'all able to see that if you took the cosine of theta, it would be adjacent over hypotenuse, which is F parallel over F? Therefore, F times cosine theta would just be F parallel. Anybody have any questions on that? Okay, so that turns out to be exactly the kind of product we want. And now we're in some position to write out exactly what this work is with this crazy new quantity. And I actually have to fix that F parallel because that was a pretty critical drawing there. So there's your F parallel right there. So that's our general formula for our work. It's work equals the integral of F dot dl, and the dot product, at least one way of writing it, is this: A dot B equals the magnitude of A times the magnitude of B times the cosine of the angle between them when they're tail to tail. There's another way you can write it as well. Let me show you that just so you'll know. One of the things we learned in chapter 3 was when we did vectors, we could actually call a vector A, and we could write out that vector A by calling the x component A sub x and then multiplying that by I hat, and then adding to it the B component multiplied by J hat. I say the B component, that's supposed to be the Y component. I don't know why I wrote B. Well, I know why I wrote it because I said it. I just don't know why I said it. All right. So the Y component times J hat plus A Z times K hat. Okay. So that's one of the things we learned in chapter 3 is that we can express a vector by writing its x component in front of I hat, its y component in front of j hat, its z component in front of k hat, and then adding them all up and you'll have a vector. Now we can also add the vector b could be written as bx I hat plus b y j hat plus b z k hat, and then a, well, let's stick to my color program. A dot b would be ax I hat plus ay j hat plus a z k hat dotted with bx I hat plus b y j hat plus b z k hat. And then we just assume, and I'm telling you it's actually true, so you don't necessarily have to assume it, but you might, as a first order approximation, assume that it obeys the distributive property because everything in algebra seems to obey the distributive property. So why wouldn't this? And I'm telling you that yes, that is the right thing to do. So what I'm going to do is I'm going to allow the first term to hit the first term, and what I'll get is ax I hat dotted with bx I hat. Oops. Bx I hat like that. And now I'll do the next one. Notice I separated it by plus. Now I've got AXI hat dotted with BYJ hat. Now I'll do the next, which would be again the first term, but this time with the third term, and I get plus AXI hat dotted with BZK hat like that. And now I've gotten at least a third of them because there's three terms in the red A vector, and I just did one of them. So now I'm going to take AY and let it hit each term. So this is going to become AYJ hat dotted with BXI hat plus AYJ hat dotted with BYJ hat plus AYJ hat dotted with BZK hat. And again, plus is separating all of them. And now I have to do the third term in A. So this will be AZK hat dotted with BXI hat plus AZK hat dotted with BYJ hat plus AZK hat dotted with BZK hat. And that really is the sum total of all the terms that you get from taking a dot product. So as I told you, it does obey the distributive property. So everything I've done so far is fair. Now, the other thing that I can do is I happen to know that the dot product is what we call a linear operator. Dot product is a linear operator. Don't worry too much about the details of that, but the linearity part is something that's kind of crucial for us. And what that means is if I did A dotted with, let's say, A, or let's say lowercase b is a scalar times b vector plus lowercase c is a scalar times c vector. If I allowed this dot product to take place, the fact that it's linear would mean that I can pull this b out in front and then just do a dot b, and I can break the sum up and do c out in front and then a dot c. So that's one of the things that linearity allows us to do. So now I can go ahead and do that here. And what I'll get is AX BX for that first term, and then I hat dot I hat like that. Well, what we learned was the dot product is the magnitude of the vector times the magnitude of the second vector times the cosine of the angle between them. So that means I hat dot I hat is 1 times 1 times cosine. These two vectors are identical, so the angle between them has to be 0 degrees. So all of this turns out to just be 1. And just to remind everybody, this all came from A dot B is equal to AB cosine theta. Notice that time I just wrote it with the letters without the absolute value bars. That's because if you write a vector letter without the vector symbol over it, then everybody understands it's just a scalar. So that's what happened when I did the first term, but look what happens when I do the second term. So the second term, the second term is AX with BY, so I'm going to say plus AX, and by linearity, I'm pulling the BY out in front, and then I get I hat dot J hat. Well, these two are both unit vectors, so I still get 1 times 1, but I and j point in starkly different directions. Can anybody tell me the angle between I hat and J hat?
Is it 90?
Exactly, 90 degrees. Very good. Because the I hat points in the positive X direction, the J hat points in the positive Y direction, and they're different by 90 degrees. And of course, the cosine of 90 is zero. So that one's going to give us zero. And you can now see that the third term, which is going to be a I hat dot K hat, that's also going to give us zero. So A, X, B, Z, I hat dot K hat again gives us 1 times cosine 90 degrees, which gives us zero. So I think you can now see that looking at how this is going to work out, we're going to get zero plus a y b y times 1 because j hat dot j hat is 1 plus 0, and then we can say plus 0 again. That time it's for azbx plus 0 again. This time it's azby, and then plus azbz times 1. So we ultimately see that A dot B is also equal to AXBX plus AYBY plus AZBZ. So that's two ways you can calculate it. I've written one. Here's the other one. A times B times cosine theta. And I'm going to box this off. And these are your two formulas that you can use to calculate a dot product. You can see also that you could, for instance, if you had a drawing of two vectors and you knew the magnitude and the angle between them, you could use AB cosine theta to find out what A dot B is. And then you could use that if you happen to know all the components of A, you could use that to find a component of B or maybe even two components of B, depending on how much information you had. So that's a typical thing that can be done. You can also, if you know all the components, you can go ahead and calculate the AX, BX, AY, BY plus AZ, BZ, which is a scalar, remember. But you can calculate all that and then say, well, that's equal to the magnitude of A, which I can calculate, times the magnitude of B, which I can calculate, times the cosine of the angle between them. So you could use it to find the angle between two vectors. So that's the beauty of this dot product. Anybody have any questions on this dot product? Big picture now. Here's the big picture. The big picture is physicists use dot products to find the component of one vector uh, that is parallel to the other vector. So if you have two vectors and you want to compare them, you might want to say, okay, well, how much of one vector is parallel to the other? Well, you should immediately think, I need to use a dot product. Not that that's the whole answer. Okay, so if you wanted to know, for instance, what is it? Well, you could look at a problem like this. You could say, okay, let's say this vector right here has a magnitude of 5 and is at 36.9 degrees. Okay. And let's say that this vector right here this is vector B, for instance. This will be called vector A, and this one will be called vector B. And I'll also add to it and say that we have a coordinate system that we don't necessarily have to have, but I'm just putting it here to make it seem a little bit more feasible. So here's the y-axis, here's the x-axis. If I wanted to find the component of A parallel to B, I'd say, what is the component of A that is parallel to B? Now, can anybody look at that vector A with that angle there and tell me exactly what that is? What the answer to the question I just said was? You might not if you don't remember these vectors, for instance. If you don't remember this particular triangle, for instance, you won't be able to get it until you do the work. Anybody recall what triangle has the 36.9 degrees? Okay. Well, I'll tell you, okay. The vector that's 36.9 degrees, or excuse me, the arrow, if you will, that's at a 36.9 degrees from another part of its triangle is the 345 triangle. So we're thinking of the triangle that looks like this. We'd have a 4 down here. We'd have a 3 up here, and then we'd have 5 right there, and this would be the 36.9, like that. So when I ask the question, how much of A or what is the component of A that is parallel to B, what I'm asking is what fraction of the total vector A is parallel to B? Well, the fraction of it is the actual 4 component. So we should expect, if I do this calculation, to get 4. So how do I do this calculation? Well, what I want to calculate is the projection. That's just a fancy word. The projection of A onto B. Okay. And I can make up a formula for that right quick by writing projection uh, with a subscript B and a value of A. So you're sort of looking at it like it's a operation that's operating on the vector A, like that. But it also has to do something with the vector B. Well, what we really want is this little horizontal component right here. So I know it has to involve my A dot B. So I'll just write A dot B up top. Well, that is A times B times cosine theta. So I look at this triangle and see that if I took the 5 and multiplied it by cosine of 36.9, which is theta, then that would be right. So this top is A dot B, but it's also AB cosine theta. So I want to get rid of the B part. So I'm going to take down here and divide by the B. That would make the actual quantity just A cosine theta. But I also need it to be a vector because the projection, I want an actual vector, and I want that vector to point in the B direction because I'm asking for the part of A that is parallel to B. So I could put a B out here and that would make it point in the right direction. But by doing that, I've now increased the magnitude of this projection by a factor of b, and it was already the right size. So now I've got to put a b squared down here in the bottom. So that turns out to fix it. So if you actually did this process, if you went through this calculation right here and said the projection of A onto B is A dot B over B squared times B, let's say the magnitude of B is, and it doesn't really matter at all. I'm going to say the magnitude of B is 13. Okay. Don't even worry about the units. We'll just say they're pure numbers or something. So if I take A dot B and do the calculation like I said, then A dot B would be 5 times 13 times cosine 36.9. So 5 times 13 times cosine 36.9. That gives me 51.97. 9795, in fact. That's the A dot B. Now I need to take the magnitude of B and square it. So I'm going to take the 13 and square that. And then I'm just going to multiply it by the vector B. Okay. Well, if I take the 51.9795 and divide that by 13 squared, I get 0.307. But if I instead just divided it by B, then I could look at it another way. So let me regroup and show you which way I'm going to look at it instead. It is supposed to be B squared down here, but one thing that hopefully you already know, but if you don't, it's a good time to learn it. I could take the b down here instead of making it b squared. I could put 1 under the 51.9795, and then I could take the other and put it under the b vector. And this whole quantity is what we call the b unit vector, or b hat. So guess what? Anybody recall what I told you the projection of A onto B was in this case? Anybody remember what the number was? You can look over here if it helps. Nada? Okay, well, it's supposed to be 4. So if I take this 51.9795, and I divide that by 13, I get 3.998. So that's essentially 4. So that's what I mean by the dot product can be used to pick off components of one vector that are parallel to the other. There's another one we'll use, and we'll learn about it later, and it's called the cross product. That one actually takes two vectors and spits out a vector, whereas this one takes two vectors and spits out a scalar. That's why it's called the scalar product too. But the other one, the cross product, that allows you to find the component of one vector that's perpendicular to the other vector. So that's what I mean by the big picture. Why do we have dot products and why do we have cross products in the physics world? It's because when we need to find what part of two vector fields are parallel to one another, we should do some kind of dot product process with it. So anybody have any questions on that? If you turn to the end of chapter 7, you'll see very early on a bunch of problems where you can take dot products and stuff like that. I'd recommend you do as many of those as you can, especially the odd ones, because the answers are in the back of the book, and it usually don't take you a couple seconds to do any one of them. But your homework will have some too. But if you finish your homework and still think you don't understand dot products, that'd be a good time for you to consider doing some of those other problems. I'm sorry, I just realized my chat window wasn't up, and you guys been answering me the whole time. Good job, Aiden and Ruse and all you guys. All right, now that we've talked about what this dot product is, now I can go ahead and show you some simple cases of work. Okay, so we had worked out that work is equal to F parallel times D for a constant force. So that's like the low-hanging fruit. That's the easiest one. As the force varies from place to place, you might have to do at least a sum of a bunch of different smaller dot products, or you might have to ultimately do an integral. But right now, what I want to do is I want to solve this problem. So let me stop sharing this screen for a second and share another screen. The screen I would like to share is this one. So you're looking up here at example one, and you guys might want to take a screenshot of that because it's not going to be actually in my notes. So you can get it off the screen if you want to. I'll try to put it in my notes later. I'm not sure I'll get around to it, but it's a kind of a hassle. But anyways, a person pulls a 60 kilogram crate 35.0 meters along a horizontal floor by a constant force FP equals 100.0 newtons, which acts at 36.9 degrees above horizontal. The floor is rough enough to cause a 45.0 Newton friction force that impedes the crate's motion. Determine A, the work done by each of the by each force acting on the crate, and B, the net work done on the crate. So that's what we're trying to do here. I'm going to jot down these numbers. I have the mass of the crate is 60.0 kilograms. I have the displacement is 35.0 meters. I have F sub P, F sub P is equal to 100.0 newtons. The underlined zero just is me showing you guys or reminding you guys that I'm using all three sig figs. So the one and two of the zeros are significant figures. We have an angle theta is equal to 36.9 degrees, which hopefully jogs your memory. And we have a friction force is equal to 45.0 newtons. So what all this looks like is a box, and this box has a force of M times G, which is 60 times 9.8. So 60 times 9.8 gives me 588 newtons acting this way. We also have a normal force acting this way. We know that this thing is going to slide along a somewhat rough floor, and it's going to do so in such a way that its displacement vector is d, and the length, of course, is 35.0 meters. Now, we also have a force acting on it, and this force doesn't fit one of our coordinates, so I'm just going to draw it in black. And this one is the 100.0 Newton force. And this angle is 36.9 degrees. Now, this again has the 36.9 degree angle, so that should make you think the 345 triangle. So you're looking at the hypotenuse, and the hypotenuse is supposed to be 5, but it's 100. So obviously, you've multiplied the 5 by 20. That means the 4 should be multiplied by 20 and the 3 should be multiplied by 20. And remember the small angle, which is the 36.9 one, since it's smaller than 45 degrees, that one is always opposite the smaller side. So what that tells you is that this component right here is the 3 times 20 or 60 newtons. And this one right here is the 4 times 20 or 80.0 newtons. Okay. Now, if you didn't remember that, that's okay. You can go ahead and just use your trigonometry to figure out what those components are. But be advised, you definitely have to figure out what those components are. Okay. You can't just not do that part. So I'm treating that as my x-axis. I'm treating that as my y-axis, just so I can make it nice and easy to address. And I'm going to say that this force right here is my friction force, and that one was 45.0 newtons. Okay. Now, what I'm going to do is I'm going to take the summation of the forces in the y direction is equal to mass times acceleration in the y direction. Now, this thing's going to be horizontally going over. I need to show you my screen again in a second, so let me do that too. But this thing is being pulled along a horizontal surface this way, and we're not expecting it to be doing any up and down, up and down, up and down. In fact, the y coordinate should more or less stay the same. Therefore, the y isn't changing, and neither is the velocity. And since the velocity is not changing, neither is the acceleration. And in fact, the acceleration has to be zero. So I'm going to go ahead and say equals zero. And from this, we get the normal force plus 60.0 newtons minus 588 newtons is equal to zero. That tells us our normal force is 588 minus 60, which would be 528 newtons. So, yes, as I told you, using work and energy allows us to not do as much vector stuff, but you're not getting rid of all the vector stuff. You still have to do some. All right, now that we have that and you've seen how this problem's worked out here, what I want to do now is stop sharing that and go back to sharing my iPad screen so you can see what I've written down. It was supposed to mostly just be the data and a drawing. I now have it so you can look at it and see how I interpreted that problem. When the problem comes back up, while you're looking at this, I'm going to read that example to you again. It says a person pulls a 60 kilogram crate 35.0 meters along a horizontal floor by a constant force FP equals 100 newtons, which acts at 36.9 degrees above horizontal. The floor is rough enough to cause a 45.0 Newton friction force that impedes the crate's motion. Determine A, the work done by each force acting on the crate, and B, the net work done on the crate. So hopefully y'all now can make some sense of the diagram and the question and see how they're related. So I've drawn out a D type vector. That's my displacement vector. You can see its length is 35 meters, and you can see all the vectors that are on there. So first off, I want to calculate the work done by each force. So when the force is a constant, it's just force, the component of it parallel to the displacement times the displacement. So I can do in part A, I'm going to say the work done by FP. Okay, remember FP is the 100 Newton force, and that is equal to the component of FP that is parallel to D times D. Can anybody look at the diagram and look specifically at the 100 Newton force and tell me what is the component of the FP force that's parallel to D? How many newtons is that? Anyone? Ah, crap, I lost my chat screen again. Let's see here. Turn on my chat. Turn on my chat. There it is. Okay, does everybody see the work FP equals the FP parallel to D? So what we're focusing on here is this force right here, because that's the one that happened to have the 100 Newton magnitude, right? But we have to break that up into X and Y components. Really, all we had to do is break it up into components parallel to D and perpendicular to D, but that happened to be consistent with X and Y as well. So is this component, is that parallel to D, or is this one parallel to D? Very good. Yes, 80.0 newtons is the force parallel to D. And now all we have to do is multiply that by the D. And this is going to give us not only the answer, but it's also going to give us the unit that we use for work and energy, which I'll tell you in a second. So 80 times 35, that's 3 sig figs each, gives me 2.800 times 10 to the third. And it's Newton meters, Newton times a meter, but that's defined to be a joule. So 1 joule is defined to be 1 Newton times a meter. And whenever we're working with work and energy, we keep it in terms of joules, not Newton meters. Whereas, sometimes some of you might done it in lab already. Specifically, if you do a torque lab, you'll see a Newton meter is also the unit of torque, but we always leave it as a Newton meter there. Whereas in the energy chapter, we leave it as a joule. Okay. So we've got our work done by the FP. Now I wanted to see the work done by the FN. Well, work done by the normal force is equal to, this case, we don't necessarily know the components, so I'm just going to write the normal force times D times cosine theta. Now, the normal force for the normal force, its magnitude turned out to be 528 newtons. So that's the F. The D turned out to have a magnitude of 35.0 meters. But then, can anybody tell me what angle is between the normal force right here and the displacement vector right there? Remember, they're just supposed to be tail to tail, so you could draw the D vector right here. Oops, I thought I had it on the little highlighter, but I did not. You could draw the little D vector right here and the Fn vector right here. So what is that angle? Yeah, there you go. Yes, 90 degrees. So what I'm going to write here is times the cosine of 90. And all you good little trig students, I'm certain, recall exactly that cosine of 90 is 0. So we get 0 joules for the work done by the normal force. The work done by the weight, which would be mg, that's just mg times d times the cosine of the angle between them. So the mg we already know was 588, and the d we know was 35.0 meters. And now the cosine is, anybody want to guess on that one? What's the angle between those? That one's going to, you could make an argument that maybe it's supposed to be 270 or something like that. But the main thing is it's certainly a multiple of 90, and it's an odd multiple of 90. So it's definitely going to be 0. So the cosine of 90 degrees is 0. So the work done by the weight is also 0. Now we've got one more force left, and that's the friction force. So the work done by the friction force is equal to the friction force times the magnitude of the displacement vector times the cosine of the angle between them. So the friction force is 45.0 newtons. The displacement has a magnitude of 35.0 meters. And then, anybody want to take a guess what the angle is between the 45.0 Newton vector and the D displacement vector? Give you a hint. It's not 0 and it's not 90. Very good, Charles. Yes, it's a whole 180 degrees because the D points this way and this would point all the way back this way. So, yeah, it's 180 degrees. So cosine of 180 turns out to be -1. So I get 45 times 35, and that gives me 1,000 or 1.575 times 10 to the third, and it's negative, and it's joules. Okay, so that negative is very important. That tells us that in some sense the displacement is overcoming that force. So the displacement's winning. The net motion is to the right, even though the friction force is to the left. So whenever you find a force acting one direction, and the displacement mostly acting 180 degrees the other way, then you expect that work to be a negative quantity. So we now have our four answers for part A. And for part B, they want to know the net work. So this is part B. W net just means add up all those other ones. So it's the work done by FP plus the work done by FN plus the work done by MG plus the work done by the friction force. So if we add all these up, I get negative 1,575 plus 2,800 joules, and that gives me 1,225, which again, for sig fig reasons, I'll say is 1.225 times 10 to the third joules. So that's the total work done. Anybody have any questions on that one? All right. So let me introduce you to something. Now that we've done this work net, that work net is the sum of all the possible works that can be done, but we can look at it another way too. So this is going to be about something we call the work energy theorem. Okay? We can say, for instance, that work net is equal to work. Well, let's write it this way to be a little bit more fancy and correct. The summation from I equals 1 to n of W sub I. That's a way of doing it, right? You add up all, if there's n forces or if there's n things doing work on it, then you add up the work done by each of the n things. But another way you might consider doing it is say it is the summation of the forces times, let's say, I'll call it DL or delta L, something like that. So we could take and sum up all those little pieces like that. But in order to do that, I would divide it up into infinitesimally wide little intervals and then take an integral. So this is another way to go about calculating the net work done. We don't have to think about the work done, calculating it first. We could say, wait a second, let's take the sum of all the forces and just apply that to do the work. And then that would also give us the work net. Well, when you do that, then you can make use of Newton's second law, which says the summation of the forces is equal to m times a. So if we did that, we would get the integral of, now in place of the summation of forces, I'm going to say m times dv dt because acceleration is the derivative of velocity with respect to time. And instead of well, I'll still call that just plain dl. Oops, might help if I put it on marker. Multiplying this or dot producting it is the cleaner way of doing it. Dot dl like that. That's what we now have for our integral. But I'm also free to move dv and dl back and forth. Multiplication is, you're allowed to multiply in any order you want. So in this case, I'm going to do the integral of m dl dt dotted with dv. So all I did was trade the position of dl with the position of dv. Can anybody tell me, and it might require you to think about the units first, can anybody tell me what dl dt is?
Is that speed?
Yep, it's speed or velocity, either one. Yep. In this case, we're not using x necessarily, we're using a distance L, but it's still a distance over time and it's still the instantaneous rate of change of it. So yeah, it's absolutely the velocity. And now what you see is we have the integral of mv dv. Well, that's easy enough. That's just 1/2 mv squared. And we're going to evaluate that from v at t equals 0 to v final. So what we end up getting, of course, is the work energy theorem, which says the net work done on any system has to be equal to the change in kinetic energy. And that change in kinetic energy is 1/2 m v squared minus 1/2 m v zero squared, which, like I said, is just delta K, where we've now defined kinetic energy as 1/2 m v squared. So this is a new equation that we found. It's called the work energy theorem. And the work energy theorem says that the net work on any system from one time to another will always be equal to the change in kinetic energy. No ifs, ands, or buts about it. There's no way you can change that. Okay. And in doing so, we were able to stumble upon how we got a idea of what the definition of kinetic energy would be. It's 1/2 mv squared. And that is true, by the way, but it's not true if we start getting the speeds around 1% of the speed of light or higher. That's a rough uh, estimate of when it's dangerous to use non-relativistic equations. But as long as you're well under 1% of the speed of light, you're probably in pretty good area using k equals 1/2 mv squared. If you were dealing with a higher speed than 3 times 10 to the seventh meters per second, then you definitely want to use the proper formula from relativity, which I could give you if you wanted, but you don't really care. Okay. So that's the work energy theorem. That's the change in kinetic energy. And you might even imagine that if you imagine the work net being equal to the work done by the friction force of skidding tires, then you could actually calculate how fast the car was going before it got into a wreck by looking at the skid marks. Because the skid marks start when he hit the brake, the person hit the brake so hard that it started to skid, and it came to a stop. You can measure out how long that is. That's the distance over which it was traveled. The actual force is pretty constant during that time, and therefore you can say whatever the friction force is, it's a constant. So I just have to multiply that friction force times the length of that skid mark, and that'll give me the magnitude of the work done by the skidding of the tires. Well, that work done has to be equal to the change in kinetic energy, which, if it came to a stop, obviously the final kinetic energy is 0, but the initial kinetic energy is what you want. So you can look up, for instance, what types of tires and what type of road surface it is, and that'll give you a good estimate of the coefficient of friction. And you could also look up what type of car it is. That would give you a good estimate of the mass, and therefore you could find the normal force, and you could use it again in 1/2 mv squared to find the final velocity. So that's really all that it takes for a police officer, for instance, to figure out how far or how fast a car was going when they got in a wreck. But that's just one of the many simple applications you can do. Of course, you're going to see me here again Wednesday, and probably I'll be sitting in the same place, which doesn't really matter. But the fact is that I'm sitting. That's what matters. So I'm sitting here. My velocity is 0. A week from or 2 days from today, I'll be doing this again on Wednesday, and I'll be sitting still again. So my kinetic energy then and now are both 0. So my change in kinetic energy is 0. So no matter what I did between now and Wednesday, you can definitively tell me that the total amount of work done on me in that time period will be 0, because the kinetic energy before and the kinetic energy after were both 0, and 0 minus 0 is 0. So the total work must be 0. Any questions on that one? All right. Well, I want to show you, there's another example I was going to do, but before I did that, I want to go ahead and get you to a place where you not only knew about what the dot product is, which I feel pretty good about what I showed you there, but I wanted to show you how you can calculate exactly what a potential energy function is by using the work. So what we do is there's a quantity called potential energy. And if the force is what we call conservative, which we'll teach you about that later in this chapter, and then you'll review it again in 242. But if you actually try to work that out and figure out, darn it, I just lost my train of thought. That's what. Okay, I was talking about the working. Oh, I remember. So, uh, our ability to define potential energy is basically you got to confirm first that the force is a conservative force. And there's tests we can do on that. That's not a big deal. But once you have that conservative force, then what we do is we define the change in potential energy. So we'll say there's a quantity delta U, and delta, whenever you see that triangle, that always means final minus initial, unless they explicitly tell you otherwise. And this U is what I call potential energy. And again, there's going to be a potential energy function anytime you have a force that's conservative. And if you do have a force that's conservative, then you can define the change in potential energy as the negative of the work done by the conservative force in going from A to B, say. And remember, I said delta U is final minus initial. So that also means that is UB minus UA. Okay, so if you imagine a position A, the potential energy at that point would be UA, and at position B, the potential energy at that point would be UB. And if we can calculate the negative of the work done by the conservative force, then that'll give us our function. So that's what I'm going to do now and show you how. Okay, so I'm going to draw a vertical axis. Just call that the y-axis, and I'm going to draw a horizontal axis. Let's call that the x. And what I'm going to imagine doing is taking a mass m, and I want to lift up on this mass m with just enough force that it no longer has any more force acting on it. In other words, I just want to cancel out gravity, but I want it to be just a infinitesimal amount more, so that if a freak of nature like an atom bounces off the bottom of it, it's going to move it up a little bit. And then I'll do the same thing, wait again and wait for another little atom to randomly do it. So in some sense, I'm trying to not actually accelerate the object. I'm just making the force on it so small that an infinitesimal collision or any other small freak of nature could cause the object to lift without actually increasing my velocity in any way. In doing that, I'm sort of trying to see the minimum amount of force and work I can put in to raising the object. So that's what we're going to do. We're going to imagine that just enough force to overcome the force of gravity is going to be applied to it, so that it never really speeds up, but it does over a very long amount of time end up moving the entire distance from y equals 0 to y equals h, like that. And of course, like I said, this is y equals 0. Okay. Well, we know that the force acting down is mg. So if I put an equal magnitude force on it, and that magnitude would be mg, then I know exactly what that force is. Its magnitude is mg. So now I can calculate the work done by the conservative force, and that conservative force is gravity, by the way. The work done by the conservative force is the integral of F dot dl. That's what I told you earlier. Now, in this case, the force in principle, that g depends on how high you are above the center of the earth. But if you're really at all terrestrial distances, like say from the top of Mount Everest down to the bottom of the Marianas Trench and all those distances, g doesn't change by an appreciable amount. So this is actually perfectly fine for us to treat f as it's a constant. So I'm going to do it with vectors just so you'll have an idea. I'm going to say the integral of m times g. Now this force is uh, is the force that we're applying to it, but the conservative force is this force right here, F conservative. That's the gravitational force. And that one is, of course, negative mg. So I need to put that negative in here, and you're going to see where that's going to come into play because remember, we're supposed to calculate the negative of the work done by the conservative force. So I'm going to say the force is actually pointing down, and it's in the negative y direction, which we just reviewed is in the j hat direction. So this negative times mg times j, that gives us a force vector that's pointing down just like we expect it to. So that's exactly what we wanted. Now our dl, okay, this integral is technically what we call a line or a path integral. And when you're doing a line or a path integral in 241, it's almost never a problem, okay? But just so you'll know, the rule is when you do a line or path integral, you either got to let the dl point in the direction that you're actually integrating, or you've got to let the limits of integration point in the direction you're going. Only one of those is allowed. And which one you choose, like if you choose the limits of integration to show which direction you're going, then the dl is just going to be in the positive coordinate direction. Alternatively, if you choose the DL to point the direction you're integrating, then you make that point the same direction that you're integrating, but you let the range of integration go from small variable to large variable. Okay. Most of the time, you do that blindly and get the right answer. So that's why it's not that big a deal. But I just wanted to teach it to you. And by the way, it is in the back of your calculus book. It's something that occasionally some professors might get to in their third semester of calculus, but I've never known of a school that could. Okay, so here's the integral of negative mg j hat. That's my force. My dl, I'm going to integrate from y equals 0 to y equals h. That's in the up direction. So I'm going to let my dl show which direction I'm going by writing positive dy j hat, just like that. Okay, so I use the DL to show which direction I'm going. That means by default, I have to do my limits of integration from small number to big number. Well, the small number is y equals 0 to the big number, which is y equals h. Now that I have that, I'm going to use the linearity of the dot product. And notice that that means I can pull this dy out in front of both j hats, and I'm going to get integral of negative m times g times dy times j hat dot j hat. And of course, j hat dot j hat is 1 times the cosine of 0. So that's 1. And this is from 0 to h. So now I see the mg is a constant. I'm going to pull that out in front with the negative. So negative mg times the integral dy from 0 to h. And lo and behold, you're going to get negative mg h minus 0. So that's the work done by the conservative force. The delta U, which is the negative of the work done by the conservative force, that is going to be a positive mgh plus, or excuse me, I could say minus mg times 0, just so I make it in the form of UB minus UA. So now that I've done that, I can see that my potential energy function U is just equal to m times g times y. And that is it. That's the actual potential energy function. At least if you're roughly less than a whole Earth radius from the surface of the Earth. If you're closer than an Earth radius from the surface of the Earth, then you're close enough for G to be considered constant. Otherwise, you have to use the gravitational formula. Anybody have any questions on that potential energy that I just derived? Okay, now that is definitely not something you're expected to be able to do, but if you went on to become a engineer or a physicist or something like that, and you discovered some new kind of force, you might want to figure out how to see if it's a conservative force. And one such way of doing that is checking whether the work done and going from one point to another is independent of the path and in fact equals a change in potential energy. If that's what you use, then you could actually use that and try to figure out what the function u is. And that would be how this derivation played out. The more important result here is just that potential energy when you're close to the Earth's surface can be handled by mgy. And not only that, it doesn't matter what you call the zero of height as long as you're consistent in any one problem. So, for instance, if you're working a roller coaster problem, you can take the lowest spot on the roller coaster and call that zero height. Or if that's 20 feet above the ground, you could call the 20 feet down, which is 0 point. You could call the height of the ground zero, and that would work out too. So, you guys are done. You're free to go. Make sure you chat me your first and last name if you haven't done it already. Thanks for coming. I'll wait for the last person to leave in case anybody has any questions. And don't forget to get your homeworks knocked out and your online tests knocked out. All right, good deal. How's it going, James? You have a question, sir? I don't see him typing. I don't believe Mr. Isaac is here, so I am going to go ahead and call it. Let's do a stop share. And I'm going to say, oh, there he is. He did there. No problem, James. Did you have a question before I go, bud? I guess not. All right. Well, have a good one, everybody. It was nice seeing you. Thanks for coming. And physics rocks.